Let's say this was a graph that we got for something oscillating. A mass on a spring would work. What will the function be that describes this motion? The position as a function of time. So the amplitude's 8 centimeters. We know this is a negative sine graph. Perfect. We just need to figure out the omega value. What's the period? 2 seconds. Period's the amount of time to complete one cycle. So period's 2, frequency is 1/2, omega is 2 pi times frequency, so yes, pi. Now you can write your units in there if you want, or if you don't write units on your pi, it's assumed that it's radians per second. So that would be the function of our position as a function of time. Tell us where our object is at any point in time that we're interested in. So little t is any time, whatever time you're interested in. Big T, capital T, is specifically the time it takes to complete one oscillation. Again, velocity would be the derivative. Something interesting about velocity. Let's take the derivative of this. Derivative of this will be negative 8 pi centimeters per second cosine of pi t. With the position function being negative sine, the velocity function ends up being negative cosine. So where does the velocity function start? If time is equal to 0, now, sorry, the scale's not going to be exact. The scale's different. Sorry, not the prettiest sine wave there. When the position is 0, the velocity has a maximum value. When the velocity is 0, the position has a maximum value. When the position is 0, velocity has a maximum value. Think about it in terms of conservation of energy. When the position is 0, when it's at equilibrium, it will have the most amount of kinetic energy. But when the position is maximum, so it's down as far as it can go, the energy is elastic potential energy. So the object's not moving. There's no kinetic energy at that instant. So in terms of energy, maximum displacement means all potential energy. No kinetic. So it has no speed. V is 0. When it's at equilibrium, when the elastic potential energy is 0, it's kinetic. So it's moving fastest. Another interesting thing. We take the next derivative, we're going to get the acceleration. If my position's a negative sine graph, my velocity is a negative cosine graph, but my acceleration is a positive sine graph. It'll start at 0, reach a maximum, go back to 0. It's exactly opposite the position. But if you remember, the force of the spring is negative kx. Negative because it's trying to oppose whichever direction it's been stretched or compressed. The acceleration always will be in the opposite direction of the position. If my spring has been stretched downwards, it's trying to pull my mass upwards. Okay? That's why they're exact opposites of each other. But the acceleration and position are zero at the same time. One has a positive maximum value while the other has a negative maximum value, and so forth. Okay. By the way, what does this number represent? Maximum acceleration. Exactly right. The 8 pi centimeters per second would be the maximum velocity. This is the maximum position. The negative sign goes with the sine or cosine part of the function. Just tells you whether your function's going up or down. The numerical value is the maximum of whatever your function is describing.